Hey guys, what's up? Eddie Alho here with KissAnalog.com. All right, today we're going to jump into kind of my specialty, switch mode power supplies. We're going to talk about the flyback converter. The flyback converter is arguably one of the most common converters, isolated converters. Whenever you need isolation, galvanic isolation from input to output, like let's say you're taking power from the AC wall and you want to power something with DC voltage, you'll use isolation, right? Galvanic isolation to separate the earth safety ground from your secondary grounds, okay? So a flyback converter is a great way to do that. Now it's still a DC to DC converter, even though it's taking AC power and converting it to some DC voltages for your whatever. You know, the old-fashioned televisions, the CRT tubes, they had high voltage in there. And a flyback converter is commonly used in those kind of applications because you can bump the voltage up high easily with the flyback. So if you need high voltage on the secondaries, that's a great reason to use a flyback. The other great reason is sometimes it reduces cost. You don't need that output inductor that you need on a Ford converter, let's say, and you don't need a diode. So you save yourself a diode and an inductor on the output. You need a diode, but you don't need two diodes, okay? So they can be less costly and, you know, make your circuits a little bit smaller, so on, okay? Now there is a power limit to that. As power goes up, say over 100, 200 watts, then you kind of want to switch to a Ford converter, you know, something like that, okay? But flyback converters for lower power are awesome. They make your circuits pretty small, limit the number of components you need, all right? So let's just take a look. Have my trusty whiteboard. I hope you guys can see it. All right, guys, so I simplified it, of course, but I'm showing the main components. We got the control IC controlling the switching FET, right? We have a transformer. And then we have our secondary side, and this is our primary side. So primary ground, secondary ground, galvanic isolation. We would probably use an optical coupler in here to take voltage to feed it back to the primary side to control the secondary side. Didn't show that, so that's simplified. Didn't show the input circuit. You know, even though it's coming off AC, it's still a DC to DC converter because we would take the AC, go through a bridge rectifier, a bulk capacitor, and we would have our DC bulk voltage here. This guy would be working off a capacitor and running that way. Now, with active power factor correction circuits, we would have a PFC providing, say, 400 volts over here. And then we would be converting this, okay? Now, this eval card I have back here, it takes AC voltage, bridge rectifiers, it puts in a bulk capacitor, does this, and provides 12 volts, okay? So we're going to take a look at that in a moment. I'm going to show you. We're going to power it up, just look at the output and look at the voltage. I think we're going to look at the voltage right here, okay? We're going to watch it turn on and off, okay? All right, so how's this guy work and why is it different than a Ford? If you know what a Ford converter is, if you don't, look at my video on Ford converters or active clamp Ford converters, okay? But on a Ford converter, the dot would be up here. So when this turns on and energizes the transformer, as it's being energized, that energy, it'd be plus plus, so we'd have current flowing as it's being energized, okay? Then the switch would turn off, and there'd be another diode. It'd fly back. There'd be an inductor over here, and that current would continue to flow that inductor, and this flyback, sometimes it's called flyback diode, would help that current continue to flow. That's Ford converter. So it'd have an inductor, another diode. Flyback, you simplify things. This is your inductor. This transformer acts as your inductor as well. Because the way it works is the dots are reversed. So as this guy turns on, this guy's getting energized. This is plus, this is minus. No current's flowing. So he's just being energized. So what makes that different is that this guy's storing energy. So he has to, that's why the power can be limited, because you know, to make something, say 400, 500, 800 watts, it'd have to store a bunch of energy. But it's storing energy, and then when this turns off, then the polarity here switches over, the polarity here switches over. So all of a sudden this is plus, Now that energy can provide power to the secondary, okay? On this side, it's flipped over, and so what used to be, let's see, VN, let's say it was 400 volts. You'd have 400 volts here as it's on. When it's off, that 400 volts gets flipped over. Now it's off, so the whatever's applied here, the 400 volts would be across here, plus this 400. You have 800 volts here, a lot of voltage. The other thing is there'd be leakage inductance that would cause a spike over here. Okay, that's that kickback energy. And so there'd be a snubber, maybe a snubber across the transistor, maybe that as well as a snubber or clamp across the winding here. One or both, okay? I just simplified this, of course. And yeah, so that's your flyback converter, guys. Simplified converter. We're going to come over here and take a look, but before we do that, let's go look at the data sheet of this eval card, and we'll also look at the data sheet for the control chip that's running it just quickly, okay? Just kind of show you that. Now, one thing I can tell you, well, here, let me keep this up here for a moment. There's also an active clamp flyback, and this eval card is actually set up that way. So we're going to look at that first, okay? Yeah, it'd be kind of cool to watch this first and then convert the board over to an active clamp so you can see the advantage of the active clamp. But the board came set up for the active clamp, which is actually kind of good. It takes a few more parts. Instead of having that little clamping circuit, which would have been a diode and a capacitor with the, let's see, diode, capacitor, and resistor with this a typical flyback, we're going to add a FET in there, much like the active clamp forward converter. So if you haven't seen my video on that, maybe you should go watch that. And then here, so let me explain. I think what we're going to do here is I'm just going to introduce this here. I'm going to show you the data sheets and that. We're going to look at the waveforms on this guy. We're going to look at the waveform on that transistor and the output, I think. The next video, I was thinking that we could look at more waveforms, talk about more of the mechanics, and see visually how this thing's looking, okay, compared to what the schematic looks like, and just get a better feel for the mechanics and how things are working, okay? And then we could do another video, maybe microsim, where I do a simulation, and we could finally get to a video where we feel pretty good about it and we want to know how to design that transformer, okay? We want to know how to design the circuit, the trade-offs on the different kind of parts you'd select. So we can do all that. Let me know in the comments below. Give a like to the video if you want to see that kind of stuff, if you like these kind of videos, okay? Typically the design videos I do, they get less views and less likes and stuff like that. And this is kind of my specialty, so I really like to teach this. I think I can, after several videos, you guys could feel probably pretty comfortable designing one of these yourself, okay? Let me know what you think. The EMI filter, that might be a design video on its own, but I'm talking about the flyback portion. Yeah. Which would be the bridge rectifier selection, the bulk capacitor, and everything else. The EMI filter, I should do a video on that regardless. Anyway, let me know what you guys think in the comments section down below, please. Like the video, that'll give me a good idea. And yeah, I'm going to try to keep this short, this first one, just see if I can get more people interested in this. So let's jump in, look at the data sheet. I'm going to go pretty quick. I'm going to just point out some highlights of this board. I'm going to show you the board on the bench here. I'm going to show some of the highlights of it real quick, and then a waveform, okay? So hopefully if I keep this video short enough, get enough people watching it, we'll find out if you guys like it. All right, guys, so thanks, and let's come over to the bench. Well, sorry, first let's go look at the data sheet, and then we'll come over to the bench, okay? Let's do that. All right, guys, just wanted to show you the Texas Instruments website, the UCC3580, and there's several models. This is the -4. We'll go over the different models in another video, and just quickly, you can see there are two $2.66 a piece, individual. So if you buy one at a time, so they're not very expensive actually. All right, guys, and here is the data sheet. Now, Texas Instruments bought Unitrode, who were the king of these kind of chips way back when. That's why the U for Unitrode. And then these are the UCCs. Now, you notice there's a 35, 25, and a 15, right? The 3 is the like the commercial version. The 25 is like the industrial version, and the 15 is the military version. So it's, you know, different temperature ratings and so on. So we're just looking at UCC3580s, okay? And here's the 4 different dash numbers. So it's a single active clamp reset PWM for pulse width modulation, okay? So here's some of the features on the left. I'm just going to go over this real quickly because this is just kind of an introduction, okay? This is the guts or the block diagram of what's inside the chip, okay? So that pretty much covers it all right there. Just got everything in. See, there's the bottom of it and there's the top, okay? So you got, you know, your oscillator, right? This is a ramp generator. This is kind of something I'll talk about, but basically this FET turns on, starts to charge up a capacitor and builds a ramp, okay? So here's your error amplifier. Here's a soft start, shut down. This is look at your line voltage, which is, you know, converted to DC voltage. And here's your VDD input. And this is the turn on right here, turn on, turn off thing. So it has some hysteresis built in. This little S curve thing inside here means hysteresis. So, and you can see that same thing with the line voltage as it's monitoring the voltage coming up, okay? Has a built-in reference voltage down here, 5 volts. And here's some of the different versions, whether you want undervoltage lockout to be 9 volts or 15 volts. You know, you get dash 1, dash 2, dash 3, dash 4, and whether the output to is normal or inverted. So that's why you get 4 different versions. And so then you have your output drive and output drive for number 2, okay? There's a delay you can program, and here's your clock output in case you want to sync up to things. So that's the guts. There's a description. Reading through a data sheet like this can tell you a lot about the chip. Here's your basic block diagram, okay? Now this is a basic diagram of a forward converter. You can tell there's 2 diodes and an inductor. And if you look at the dots on here, they match. As this transistor down here turns on, he's pulling current through this. This makes this is plus, and it converts into forward action, okay? There we go, active clamp forward converter. And down here, we'll have, I think, an example of the flyback. Yep, offline active clamp flyback. And you know, when you're coming off the AC line, that's why they call them offline. So, you know, basically, they're working off your line after it's been rectified to DC. See, VN DC, 85 to 400 volts, okay? All right, so up here, we have our transformer, T1. We have Q1, the transistor turn on. R is just a sense resistor to measure the current going through that, okay? Then we have our control chip, and then we have our output. See, a single diode and a capacitor. Now, this is the feedback circuit over here on the right, so it looks like it's more complex, but when you break it down into groups or function areas, then it becomes a lot simpler to look at, okay? So there's really not a lot to it. This is essentially showing this thing. You can use this as a synchronous rectifier on the output. So an output transistor, inductor, say on a forward converter, you could use this chip to do that as well. All right, okay guys, jumping over to the eval card that I have here on the bench. Here's the user guide, okay? And you can read through this. I'm just going to show you real quickly. Here's basic setup, okay? Isolation transformer, variac, and here's demonstration board and a load, okay? and then your scope and all that kind of stuff. It's kind of funny they point out Tektronix stuff. It's funny whenever I see people say, oh, you got to use flukes for things because they say to use a fluke. It's like, no, like Tektronix and fluke were always commonly used, but yeah, it's just an example. It doesn't mean because you see it in a setup or test guide that you have to use those instruments. And then this eval card is set up in two different ways. This is active clamp. So up here, QA, you see this transistor right here, and they put this inductor in here, and I'll explain all that and why they do that. And here it works with this capacitor. So now let's just go down to look at the normal flyback. So we can configure this board to work in both configurations, okay? See, a normal flyback would have a snubber. See, the diode, capacitor, and resistor just have these parts, okay? So that's just a clamp that high voltage is going to hit this drain. It's too bad they don't give example waveforms in here, but I'll tell you what it is. In this circuit, you would see kind of a ringing and that on top of this waveform would kind of look a little bit nasty and then kind of square off and kind of change. Where in an active clamp configuration, the voltage on the drain looks much more compressed. It's not ugly looking, it's more rounded or squared off. It's not really squared off, it's kind of rounded on top, and all that energy that you normally see in ringing and spikes and stuff, it just gets all kind of smushed down smoothly. So it helps protect this guy. But honestly, the most important feature is that it's great for EMI because you don't have high frequency ringing spikes and stuff, and so it's great for EMI. And also you get a bonus efficiency boost. Let's go to the bench and take a look. Okay guys, this is the setup. Here is our UCC3580 flyback demonstration from the active clamp versus hard switched demo board from TI. We're going to go over this board in a moment. I'm going to show you the amp probe looking at the input AC. I don't have ground hooked up, I just have power coming in, so I don't have the safety ground. And then I have the X-Tech over here looking at the output across this load, okay, right across here, and twisted wires up to our terminal right here, okay. Differential probe, the mix sig. This is the DP10013, and that's coming up the mix sig scope, and that'll be right here at this terminal, and then which is channel. It's right here at channel 3. Okay, then we're going to move these probes around, look at different things. Right now they're on the transistor, and they're coming up here, and they're coming to this differential probe. This is the DP750. This is the new one, the Dash 100, and set at 500, and this one set at times 50, by the way. Okay, so there's our setup, and oh yeah, and here's my variac. So here's where I'm plugged in, and then I can just adjust this voltage right here, okay? And with this guy, I can turn on or off, and I can use the meter to look at what's going to my load right here, or to the line right there, okay? So it's on, and there's line voltage, and the load voltage is 0, okay? So nice volt box. All right, so coming back to the board here, we've got the input, obviously. The hot comes up to the fuse right here, goes across the fuse, and then goes into this EMI filter. Neutral just goes straight up to the EMI filter. So they both go up, kind of wiggle through this EMI filter. These two white capacitors, part of the EMI filter down here, they are what would be tied to this ground, which I don't have connected. So yeah, the EMI filter is not going to work as well, but that's okay. Bridge rectifier, bolt capacitor, okay? And then here's our control IC, and the main switcher, the transformer, and the output, okay? Really nice capacitors out here, by the way. The polymer, aluminum polymers, and then our output here. So we'll go more into this circuitry as we go on, but that's the main portions of it. The active clamp portion is up here, the transistor and some capacitors and stuff, and then also this inductor, okay? So we'll talk about that in the next video. This video, I just want to show you this and kind of show you the power on, okay? All right, so to power on, I'll often use a plastic box like this so I don't have capacitors or whatever else blowing up, shrapnel coming up. And sometimes, if I'm really doing some power stuff, I'll wear this or just simple safety glasses. But I always try to play it safe, hook up everything before I bring power up. And so let's go ahead and do that. All right, we start over here, okay? And I'll just start dialing up the voltage, and I like to watch the voltage go into the load. And I listen for heavy current. A lot of times I'll have a current multimeter in there, or I'll be looking current through a current probe or something. But in this case, I got this thing fused, plus it's fused at the board, and I can usually hear when current's starting to come. So right around here, around 80 volts, it should start turning on. So let's come over here, and I'm bringing it up to about 80 volts, pretty close, approaching 90. Okay, it should come on. There we go. Look at that. It's starting to switch. Okay, I'm going to go ahead and freeze it. I guess I could bring the trigger up so it'll lock on better. Okay, I'm going to go ahead and freeze it. Okay, and I'll turn off the power supply just so we can look at things, see what's going on. Up here, 281, almost 282 kilohertz switching. Pretty nice. 196 RMS, this thing. We don't really care about that. It is 50 volts per. It's about 1, 2, 3, 4, 5. About 525 volts peak to peak. Pretty high, right? And then this guy here is 13.4 volts. This purple line, that's the output voltage. Okay, I'm going to go ahead and snap a picture of that, and I'll show it to you here on the screen. All right, guys, so I just kind of went kind of quick, just kind of give you the highlights, just to see if there's interest here, and give a like to the video again, comment, let me know that you want to see more videos on this topic, and I'll get you to the point, hopefully, where you will feel good about, comfortable to design your own, all right? We'll do a transformer design video. We'll do those kind of things. We'll keep each one as short as we can to keep it interesting, all right? Let me know. Give your comments. Thanks for watching. Oh, there's a super thank you button down below. That'd be a nice way to know. Buy me a cup of coffee or a beer. Or just like the video. That'd be great. Free way. Also, those links down below for equipment that I use. A lot of that's down below. And it doesn't cost you anything extra to use those. And I try to find the best sells on them. And so the links are down there. So appreciate that too. All right, guys. Thanks for watching. We'll see you next time.